On to our next presentation. We have two speakers once again for the next presentation. The first speaker is Walter Graf. He's the Smart Factory Industry 4.0 evangelist and Fujitsu Distinguished Engineer in Manufacturing and Automotive at Fujitsu. He also represents Fujitsu in the Bitkom working groups on Industry 4.0. Our second speaker is Søren Wilmsmeyer. He studied industrial engineering, and since March 2016 he is working as a research associate at the Institute of Production Engineering and Machine Tools at Leibniz University Hannover, where he heads the Department of Production Planning and Control since 2019. Your talk is titled Quantum Technology in Flexible Job Shop Scheduling, a field report using Digital Annealer. I'm looking forward to the talk and hand hereby the stage over to you. Welcome to stage, Bob.
Yeah, thank you very much for introducing us to today's presentation. I would like to change the title a little bit to have a more motivating one, and I would like to use the one "A Taste of Quantum" already today. I think because that's the key message that Søren and I would like to bring across with a very practical example we are having. When you're looking at quantum algorithms today, I think they live between two poles. One pole is certainly a very rudimentary world where you have rudimentary algorithms that typically run on today's quantum architectures already, but they have very limited practical value. They are more of scientific interest, I believe. And on the other hand, you have very complex algorithms that are much more practical from that sense, but they are not able to run on current quantum architectures. And I think this is exactly this area of tension where we live today. And this is exactly where we were using at Fujitsu with one new technology called the Digital Annealer, which is some sort of quantum-inspired optimization, or you could also say this is already delivering a taste of quantum today. I have to be very honest with you, this is not a quantum computer. It's still a classical architecture, but it is actually moving the boundary to what we would normally consider to be only addressable by a quantum architecture. And to illustrate this a little bit more, we have chosen an example from the area of flexible job shop scheduling as a real-world example. And in this real-world example, and for those of you who are not ultimately familiar with manufacturing, I would like to illustrate this in a very brief example. So consider for a moment that you have a manufacturing company that is operating in its production environment with 3 machine tools, for instance, and they are producing goods. And so, for example, there is a red product they are producing, and they start to execute on machine 0, then they process the resulting product on machine 1 and eventually on machine 2. And they do this for the green product, they do this for the blue product, and they do this for the yellow product. And as you can see, here we have now already got to an optimum solution where we have the highest possible utilization of the machinery and the shortest production time here for those four products. But in real world, as you can easily imagine, you're living in a much more complex environment. You're living in an environment where you have combinatorial problems, and this is a combinatorial problem, and the number of potential combinations is far beyond typically 10 to the power of 100, and it goes without saying that this is not possible to simply try out each and every solution to find the best one, the optimum solution, so to speak. And this is exactly where quantum architecture currently is giving some hope, and particularly I'm talking here about the quantum annealer here, where you would first of all map a problem to a quantum environment. For instance, a production plan would be mapped to a fingerprint. So the fingerprint itself would then identify exactly the production plan, and the fingerprint would be represented in the quantum world by a set of quantum bits here. So the set of quantum bit uniquely identifies the production plan in this game. And the quantum annealer then is preparing a physical environment. I'm not going into details here, but the physical environment is basically putting these qubit states in an energy environment, so to speak. And the solution to the problem is represented basically by the ground state. And this is now the art of the quantum annealer, to be able to reach that ground state and to exactly prepare the physical environment in such a way that the solution is exactly depicted by the ground state. But we all know that current quantum architectures have their shortcomings that I'm not referring here. But the question now is whether it would be possible to think hard about a classical solution where you could somehow replace or compensate the quantum intuition that I just mentioned on the slide before with a massively parallel architecture that is implemented in a single chip. And that is basically, and I know it's a little bit in a very short version depicted here, but it's in the end, it's basically a massively parallel implementation of that algorithm. And that means that you become suddenly 10,000 times faster in the finding of the solution. And to illustrate this a little bit furthermore, you can consider yourself a problem that would normally take 166 hours on an ordinary computer to complete. This is now finished in just 60 seconds. And when you look yourself at a production environment, that you can easily understand that the 60 seconds is something that everybody would invest in a planning environment, while 166 hours is absolutely out of reach. And now I would like to hand over to Søren to explain a little bit more in detail about the environment that we have tested in that sense.
Yes, thanks, Walter, for this brief introduction into the world of digital annealing, or as you said, the taste of quantum. I'm happy to now give you some insights into the use case setup and the results within our practical example. The production of the tape dispenser you see on the right-hand side was our use case. And you can normally configure it differently, and you can also add individual engraving. And this, as a result, makes each configuration unique, and each of these configurations is planned and produced more or less only once. And as a result, this means that we have more or less a perfect example of modern lot size 1 production. Within our use case, 40 jobs are produced by performing 4 operations on a total of 6 machines. Not all of the 4 operations can be done on each of the machines, but still for 2 operations, we have machines in parallel. With respect to job shop scheduling, 2 decisions now have to be made, and I think Walter already mentioned them. It's what machine should be used and in which sequence should we produce the different jobs. And you can see this is more or less a very simple setting, but there are already more than 10 squares, 287 different schedules to choose from. And this is what makes flexible job shop scheduling to one of the most difficult optimization problems in the context of production. Unfortunately, the answer to this complex problem is still often sought on the basis of the simplest production scheduling approaches. Rule-based approaches, for example, are still widespread, but very rigid. Therefore, manufacturing execution systems with more or less complex and/or AI-based optimization algorithms become more and more common, but these are still not in place everywhere. They allow for more dynamic and adaptive reactions in case of unplanned deviations from the schedule in near future. So let's say in case of a technical machine failure. But these optimizations are still not done process parallel. This is because process parallel decision-making normally still takes too long. And as a result, orders already in progress are rescheduled by the foreman on the shop floor based on his or her experience, and this can be more or less optimal. Yeah, and this is why we think that quantum-based algorithms are still used as they are still used within the Digital Annealer, can bring scheduling to the next level. To underline this, I show you the benchmarking results of our tape dispenser use case, which we generated last year on this slide. The bars in this diagram show the needed total production time for our 40 jobs. So this is not the calculation time you see here, but it is the production time for the 40 jobs. And within only 12 to 13 seconds, the Digital Annealer found a schedule that produces our 40 tape dispenser jobs 40% faster than classical rule-based scheduling. Even the coupling of rule-based job sequencing and ML-based machine allocation in an MES brings out 18% higher production times. So, and with those results, I turn the floor back over to Walter for the conclusion of our talk.
Yeah. So I think there are two aspects that we can look at. First of all, there is the aspect to compare the Digital Annealer with other classical methods, because we're still living in a classical world, that I have to admit here. But we can constitute already that we have been able to calculate the whole problem in a much faster time. And even more important, we're getting even much better results in the end. And compared to other methods, and we were running a number of benchmarks with other algorithms as well, we also found out that there is a higher scalability in the problem formulation, in this QUBO formulation that we can do. And when you look at an end user perspective at the total problem size, we also getting a higher flexibility. And this is something I would like to illustrate on the next slide. So far, you can see that we have optimized the throughput in the whole environment. But when you look at today's production environments, this is only one aspect that could be of interest. In fact, very often companies are more interested in things like delivery reliability in the end, because that has an economic impact they are seeing. And also they need the flexibility in order to change product schedules on a last minute basis, because they're getting last minute orders that are of high priority and so on and so forth. And also they would like to deal with production outages where, let's say, you have machine failures and you have somehow to recalculate your production schedule based on degraded environment, for example. And this gives you the necessary flexibility, and you see that the time and the performance plays a very important role on that behalf on the application level, and where you see how important it is to really become better in these area. When you compare, however, the Digital Annealer with a real quantum solution, which is of course not ultimately available today, I have to admit here that we are not striving to actually substitute the quantum computing here with a classical approach. So this should not be the message, because first of all, it is quite apparent that this Digital Annealer approach is quite good for combinatorial problems, particularly the ones where a near optimum solution is still sufficient, because this is the biggest shortcoming that you have with this semi-classical architecture. I would say that you have no guarantee that you're getting the absolute optimum. And this is a promise that, of course, is kept by the quantum annealer. However, the quantum annealer is not yet there where it should be. But it could be applied then also to different problem classes where we absolutely depend on the absolute optimum, where the Digital Annealer would certainly not be suited. So this is, I think, quite important to notice when we compare the two approaches. To sum it up here near the end, I can say the Digital Annealer is actually moving the boundary of what you would typically consider the quantum advantage. We are not yet there with exponential speedups and so on and so forth, but you see that from a very practical point of view, we have been able to move the boundary based on a quantum algorithm. You can easily execute every algorithm that was developed on the annealer on a later available quantum annealer that is carrying enough qubits around. And we have shown that there is really a proven relevance for a very practical application in the manufacturing industry of job shop scheduling. And with this, I would like to conclude the presentation, because I think the main benefit we are seeing here from the quantum summit point of view is that it should really whet the appetite for the real quantum advantage, because what I also sense from the very early presenters we had today, I think the biggest challenge still is to engage the industry with the still very new and basic quantum technology. And I think this is exactly the way to go here to attract more people to invest in the real quantum world. Thank you very much.
Thank you very much to both of you. Another very inspiring talk, and I think illustrating very nicely, very well, just how much time you can save with those approaches. I mean, even if you're not using the real quantum annealer yet, but you use this step in between, so to say, the digital annealing approach, even there you can already be so much faster than classical approaches. Now you have kind of you've kind of moved alongside this line already, but let me ask again, do you have, like, for certain problems, for certain applications or use cases already made, like, calculations? Okay, how much time you can save to the classical approach with the digital annealer, but how much, what a factor will it be to actual quantum annealing in the future when this will be available?
Oh, I think there are several questions inside your single question. So first of all, we have done some investigations. I think there was this other talk about the Deutsche Bahn, the scheduling optimization thing that Christian Münch and his colleague from Deutsche Bahn was actually talking about. I think that was a second interesting example. I think that the challenge with the digital annealer or with running projects with it still is that you can not really give any firm prediction of the savings already. You simply have to try it out. And this is the reason why we have also invested some time in having very quick proof of concepts available, where you can compare the existing results that you got with certain solutions and compare that with the digital annealer, get a very quick outcome, whether it's feasible to invest there in this near optimum case, so to speak. But what remains unknown is exactly where is the absolute optimum and how much speed would you gain, or how much benefit would you gain when you could calculate the same problem with a quantum annealer. But I think it's worthwhile going that direction.
Okay, we already got a comment here in the section which also goes into that direction, that you put a lot of other examples with different customers and industry on your booth. Let me use this chance then, apart from thanking you once again for this wonderful talk, and sending you off to the Speaker's Corner now. So anyone who is interested in further discussions, please engage with Walter and Søren in the Speaker's Corner.